Assalamualaikum, sir. How are you doing right now? We hope that you are doing good. So today we are from Group 2 are going to present to you the topic that are given to us, which is application of fluid mechanic, land wind turbines. So as we know, the land wind turbine is the technology that used to convert the wind energy to the electric energy. So here as appear in the screens is the abstract of our research, which is a wind turbine is known as a device that converts the wind kinetic energy into electrical energy. It also well known as renewable energy resources which has been applied for different applications. So it tells us that rather than the wind energy convert to electrical energy, the wind turbine also a renewable energy which is came from the wind itself. So it's a energy that not gonna harm the environments and not gonna give a pollutions. So right now is the introductions. So these introductions shows that 1,000 years ago, people use wind energy to propel boats along the river or sea. And now, new ways to use wind energy eventually spread around the world. Like in 11th century, people in the Middle East were using wine pumps and wine mines essentially for food productions. And also, the wind turbine have several parts. First, blade, and then they got a tower, and also they got a generator. So this part work together to convert the wind energy to electrical energy and make it useful for the people to use it. So rather than that, this wind turbines also like a Bernoulli principle or the Bernoulli effect, where instead as the faster moving air has lower pressure. This technology is function to generate electricity using the aerodynamic force from the rotor blades, which work like an airplane wing or helicopter rotor blades. So these wind turbines can operate in various speed of wind, from the very light until the very strong wind speeds. But the average electricity generated is around 80% of the time, but not always at the full capacity. So this is the general introduction and abstract. So I'm gonna give it to the Derek to continue the presents of these slides to you, sir.
Hello everyone, I'm 2200927 Derek Ng, and now I'm going to present to you the wind turbine around the world. So the first one will be horizontal axis wind turbine, which is the most common well-known wind turbine that the blades spin perpendicular in one direction and usually comes with three-blade design. And the turbine's power plant placed on greatest wind area, which is the mountain gap or high ground seashore, and is usually produce a higher voltage. So the second one will be vertical axis wind turbine, which is less popular, and the blades spin perpendicular in all directions, and the two horizontal blades looks like a shape. Then it generate electricity in low wind speed and usually used in urban environment and produce lower voltage than the horizontal axis wind turbine. So this is the rotation parts of the wind turbine. So the first one will be the rotor blade. The rotor blade is where the fluid dynamics acts on, which is the fluid flow over the blades with the velocity of fluid flow difference pressure on above and below of the blade and exert net force and giving rotational to the shaft, where the Bernoulli principle have the which means the faster moving air has the lower pressure. So the shape on the blade on the wind turbine, when the wind molecule moving around, the blade faster on the downside than on the upside with the slower pressure. So therefore, the lift and drag force makes the blade rotate. So the blade rotates the gearbox, then the generator produce electricity, cable go through the tower structure, transformer step up the voltage and into the switch yards. So these are the examples of the wind turbine technology that is being used in the world. So Now this will be the application data around the world of the installation of wind turbine to generate electricity. So the first one is China. The electricity capacity have met to 342 gigawatts, and US is 139 gigawatts, and follow up with the other country. Then this is how the wind turbine farm works, the wind farm works. So the wind turbine powers the air and go through the transformer and into the transmission line to the village or city to generate electricity. That's all from me. Thank you very much.
The next part is momentum theory of wind turbine. A simple model may be used to determine A. The power from an ideal turbine rotor. B. The thrust of the wind on the ideal rotor. C. The effect of the rotor operation on the local wind field. The analysis assumes a control volume in which the boundaries are the surface of a steam tube and two cross-sections of the steam tube. The turbine is symbolized by a uniform actuator disc that causes a pressure discontinuity in the air steam tube that is passing through it. The following assumptions are used in the analysis. First, no frictional drag. Second, a no rotating weight. An infinite number of blades. Homogeneous, incompressible, steady state flow. Uniform thrust over the disc or rotor area. And the last, the static pressure far upstream and far downstream of the rotor is equal to the undisturbed ambient static pressure. For this slide, these are the fundamental concepts of the wind turbine. So this is an example diagram, especially this model with rate rotation. The distribution of the thrust is uniform around the circumference, infinite number of blades. We can see the formula conservation of the momentum and the conservation of angular momentum. Next is Bernoulli equation, energy conserved, and the angular induction factor A prime ought to be defined as following formula. When the thrust on an angular element is calculated using the Bernoulli equation and the conservation of linear momentum, the result is shown as the formula below. To achieve the maximum power production from an ideal turbine, this shows A prime equal to 1 minus 3A over 4A minus 1. Take note that first, the calculations are still not necessary for the geometry of the blades. Second, one can find A and A prime in each part if it is assumed that the turbine is perfect and the producing its full power. Third, by integrating along the blade span-wise, the entire thrust and rotor torque can be calculated once A and A prime have been founded. This diagram is a structured disk model with no weight rotation. Based on the diagram, we can find the conservation of linear momentum is sigma f equal dp over dt, t equal negative m flow rate times u4 minus u1, t equal to m flow rate times u1 minus u4, where T is the uniform thrust exerted on the disc rotor, which can be expressed as a function of pressure change as follows: T equal to A times P2 minus P3. The next is Bernoulli equation energy conserved for actuation disc with no weight rotation. Like this formula, and connect the two equations above and specify the axial induction factor A as A equal to U1 minus U2 over U1, and we get T equal to as the follows of this equation. The thrust times the disk velocity is how a turbine calculates its power output. Hence, P equal to this and T equal to this. Typically, the power and thrust coefficient of a wind turbine rotor serve to define its performance. Cp equal to this and Ct equal to this. Take note that first, when power is being absorbed, mean velocity at the rotor plane is always lower than the free stream velocity. Second, this model makes no assumption about weight relation. Therefore, there is no kinetic energy lost in a wheeling wake. Third, calculations are not required for the blade geometry. As continue first, one may easily calculate the thrust and power production if the axial induction factor of the rotor is established. Second, maximum power is produced by the ideal turbine. The axial induction factor A for the ideal turbine can be calculated to be 1 over 3 after some adjustment. Third, it is possible to capture more than around 60% of the kinetic energy in the wind even with the finest rotor design. So this is blade elementary. This is show lift and drag forces equation. You can see FL equal to this and FD equal to this. And this is the graph of typical variation of aerofoil coefficient. This section explains how relative velocity works. So this is explain about how we can find the blade geometry equation. Lastly is tape loss factor. You can see the equation F equal to this.
Let's move on to the discussion part. First, we talk about benefits of land wind turbine. The first is wind power is a clean and renewable energy source. Wind turbine harness energy from the wind using mechanical power to spin a generator and create electricity. Next is wind power is cost effective. Land-based utility scale wind turbines provide one of the lowest price energy sources available today. Third one is wind turbines work in different settings. The explanation is wind energy generation fits well in agricultural and multi-use working landscapes. Next, we move on to the turbulent flow towards, near, and behind a wind turbine. Wind energy conversion and turbulence, you're asking. The definition is a wind energy conversion system extracts energy from the turbulent wind and while doing so creates extra turbulence. For first, the flow towards a wind turbine. The flow towards a wind turbine is essentially turbulent with wind speed variation originating from production of turbulent kinetic energy due to surface roughness. Is the flow near a wind turbine. Upon approaching a wind turbine, the wind speed decreases and the turbulence increases in anticipation of the flow disturbing an energy extracting object. So here we can see the explanation of the flow near a wind turbine. And the third one is the flow behind a wind turbine. Here is shown two figures showing the flow behind a wind turbine. The flow behind a wind turbine is subdivided in three regions, each requiring distinct modeling approaches. This is shown in figure 1 and figure 2 before. In the near wake, the flow is dominated by the velocity deficit due to the energy extraction and the vortices created at the tip of the rotor blades, resulting in a wind speed deficit and extra turbulence. In this region, the flow structure essentially depends on the aerodynamic of the rotor blades. Next is wind turbine efficiency. Here we can see the equation. Efficiency equals to net work over energy in equals to energy out, pressure out over pressure in. Usually the efficiency is defined as the ratio between two terms which are the amount of net work to the input energy to the device. Efficiency can be alternatively defined as the ratio between the derived power P out and the rate of energy flowing in the system P in. Next, we move on to the effect of turbulence on electricity production and mechanical loading. Here we can divide it to two separate definitions. First is individual wind turbine and second is cluster of wind turbine. The first, we talk about individual wind turbine. The wind exerts forces on the rotor blades of a wind turbine. When rotating, the in-plane components of the aerodynamic force on the rotor blade causes torque about the rotor axis. Similarly, the out-of-plane component cause thrust on the rotor. Turbulence now leads to time variation in the rotor shaft, torque and the rotor thrust.
Last but not least is the cluster of wind turbine. In a cluster of wind turbine, the flow towards a given wind turbine is affected by the velocity deficit and the extra turbulence due to any upstream wind turbine. Such a cluster usually is referred to as a wind farm, which is why we call the cluster of wind turbine, so we call it as wind farm. In general, this interaction leads to a complex structure of the flow in and behind the wind farm. For example, depending on the wind direction and the layout of the wind farm, regions with multiple velocity wakes and multiple turbulence wakes may be identified. So that is all for me discussing about presenting about the discussion. Thank you.